Well, good evening, everyone. It is a great pleasure to welcome you this evening. A delight to look at the audience and see people of all ages. That's always very nice. And I am Alan Schriesheim. I'm the president of the Chicago Council on Science and Technology. I'd like to acknowledge some members of our board. Paul Knappenberg, the president of Adler, and one of the co-founders, one of the driving forces behind the establishment of the Chicago Council on Science and Technology. Kay Torsion, president of Torsion Capital Management, member of the board. I'm looking in the audience and I'm not seeing another member of the board. If there is one, raise their hands. I encourage you, before I make the introductions, to fill out the form that you have that asks some questions concerning the meeting itself. Very helpful to the staff of C2ST in terms of designing future programs. I also encourage you to think about becoming members of the Chicago Council on Science and Technology if you enjoy this program and programs similar to it. We are a membership organization, and your membership is certainly more than welcome. Well, with that as an introduction, I think a week doesn't pass by if there isn't an article in one of the newspapers about what's going on at CERN, this huge machine underneath Switzerland and France that our speaker is going to talk about. Why is it there? What is it doing? What is the meaning of the results that will come out? And it is a massive undertaking that is geared to unraveling some of the mysteries of the universe. The speaker is Dr. Young-Kee Kim. Dr. Kim is the Lewis Block Professor of Physics at the University of Chicago and also the Deputy Director of Fermi National Laboratory. Young-Kee is one of the most distinguished scientists in the United States and certainly in her field in the world, or at least the world that is involved in conducting physics and such experiments. She has multiple honors, Distinguished Scholar Medal from the University of Rochester, the Ho-Am Prize, the Alfred P. Sloan Fellowship, South Korea's Science and Education Service Medal, Fellow of the American Physical Society, and a Fellow of the American Association for the Advancement of Science. I am sure that as Young-Kee continues her career, this list will get so long that whoever introduces her will probably not be able to mention them all. Anyway, with that as an introduction, I welcome Dr. Young-Kee Kim to the podium. Thank you.
Thank you, Alan. Okay, so let me I have to say about this God particle, since this is not my slide, by the way. So people ask why, this is a, Higgs particle is called a God particle. People ask why, who named that? And by the way, this is the title, God particle is the title of Leon Lederman's book. Leon Lederman is one of the former the directors of Fermilab, and he got the Nobel Prize to discover one kind of neutrino particles. I'll say a little bit about that. Anyhow, so that's the title of his book, and we had a visitor from this reporter and came to Fermilab, asked why you call it God particle. So we said, well, we have to call Leon Lederman because that's his book. So we called him, and so we asked, why did you call it? And he said, why? My publisher told me that if I call it God particle, then the book will be sold very well. So anyway, so that's behind the story. But Leon, he has so many jokes, and just he cracks jokes all the time. So I don't know if this story is really true or that's just joke. I don't know, but that's kind of story behind it. And we discussed about that just now. Anyhow, so I'll be talking about the CERN, what's it all about. You heard from Alan, so this is so you see that this is the airport, Geneva airport, and this is Switzerland side, and that's France side. And CERN laboratory itself is just small here, but these circle and lines representing the accelerators are really deep underground, almost 600 feet underground from the surface. So that laboratory is called the CERN. That stands for really European Organization for Nuclear Physics, but it was it's 1940s founded. So it's then it's called the Nuclear Physics Laboratory or research. But really, what they are doing now or last many decades is primarily particle physics. So I'll say a little bit more about what is particle physics, what kind of questions that we are going after, and also. What the CERN, this laboratory does is very somewhat similar to what Fermilab has been doing, although we have a different kind of accelerators and different approaches to answer particle physics questions. So I'm not going to say everything, only CERN. I'll say a lot about particle physics, a lot about Fermilab, so you bear with me. So just looking at, again, more, this picture give you better feeling. This is surface. This is, as I said, about 600 feet underground. There is a so-called Large Hadron Collider, or LHC. Circumference is about 17 miles. And there are a number of experiments, but two most the prominent ones, one called Atlas, that's experimental name and detector name. Another experiment called CMS. Again, in this picture, this side is Switzerland, and this side is France. Okay, now if you look at the tunnel, so these are sort of, first of all, deep underground tunnels around this area, and it looks like that. It's about 70 miles of really powerful and complex accelerators. Inside of this, the accelerators, there's a beam of protons. By the way, proton is a nucleus of a hydrogen atom. So if you start with the hydrogen atoms, you take out electrons, then you have protons. So we have a beam of protons being accelerated in the LHC, and the other beam of protons accelerated in opposite direction when they reach maximum energy. Right now, they are running each proton energy up to about 4 tera-electron volts. So what's the electron volt? Start with the 1 electron, put the voltage of 1 volt the battery. That's how much 1 electron gains in terms of energy, how much energy they gain. So now trillion is you know how big that is. So 4 trillion electron volts is what each proton carries. So when they reach that much high energy, they collide each other. So we call this kind of accelerators colliders. So LHC is one of collider, Tevatron is another kind of collider. Okay, now you see that when they collide, all this coming out from the collisions and all the tracks you saw, these are kind of ordinary particles that with the accelerator detectors, we build a surrounding that collision area and pick all the information of what's happened after collisions. So looking at the detector, you'll see the size of person with respect to the detector there. This is a CMS detector, and all the beams going through the center of this detector. Right now, this photo was taken when detector is kind of open up. while taking data. Of course, this is closed and you cannot get in, so it's very hard to take a photo at that time. So this gives you a feeling for how complex and gigantic detector is. And there's another detector, Atlas. You'll see the scale of a human being to that. So these kind of gigantic two detectors, there are actually more experiments at LSC, all together attract about 10,000 scientists and engineers for science research. So that's really powerful and a lot of international collaborations. In fact, about 100 countries are doing the research together. And US is one of the biggest community research team working there. So now let me say a few words about the accelerators and the history. So you saw that gigantic accelerator. It started with a small 4-inch diameter, the first accelerator invented by Ernest Lawrence about 80 years ago. So that one really built and invented for the research purpose. So last 8 decades, our field, this particle physics field, needed accelerators as tools for research, and we have been developing this, generation after generation accelerators. And now the world's the biggest or complex accelerators for our research, especially particle physics, are shown here. One, obviously, the CERN, the Large Hadron Collider. In America, the Fermilab is the particle physics laboratory, and we have also very complex and powerful accelerators. And also in Asia, there's one, Kee Kim and JPROC has also very powerful accelerators. And they have a different kind of accelerators, so even though we have the going after same particle physics questions, but we approach differently. So now just talking a little bit about particle physics and what are we trying to do. So our questions here are what is the world made of? So this question is about building blocks of the world and building blocks of the universe. Of course, about a century ago, we thought the atoms are really building blocks. We thought that they are the smallest things in the world. But with the help of accelerators, we were able to do something very small and smaller. We know the quarks or electrons, and they are the smallest things. They make all of us. So finding out who they are and understanding their properties, that's one question. Second question is how these building blocks, by the way, we call them elementary particles, and by construction, there are anything smaller than that, because they are the smallest things. How these smallest things interact with each other by forces and make protons and neutrons and atoms and all of us. So those are the relevant to second question. Last question is about the universe. It's a past and present. So we want to know how does the universe from Big Bang evolve to current to present, the universe. If you know that, then of course we can figure out the fate of universe or the future of the universe. So these are the questions that we are going after. So you'll see that we deal with the smallest things, and then also we deal with the universe, which is a big thing. So in some sense, we can call particle physics is a physics where the smallest and the big meet, or inner space and outer space meet. So as I said already, that accelerators enabled us to see something very, very small. So last century, we were able to see inside of atom, and we saw that nucleus is really much smaller than the atom, and nucleus and electrons make an atom. Looking at even inside of nucleus, we found that nucleus is made of neutrons and protons. They are even smaller than nucleus. With the better accelerators, we were able to see inside of neutrons and protons. Indeed, they are made of up quarks and down quarks. So that's how it goes, trying to answer the first question. Second question's related to all the forces, and we call them interactions. How these quarks bound together to make protons and neutrons, and how they are bound to make a nucleus and our cat navi or galaxy, everything we see in the universe. So these are the forces' job, and there are 4 forces in the world, in nature. They are called the strong forces, weak forces, electromagnetic forces, and the gravitational force. So that's the second question. And the level of, the tiny subject that we are studying right now, that's a scale of a nanometer. Of course, nanometers are very tiny. I'm sure that you heard that language. We are talking about nanos and nanometers. So you can sense that how small things that we are studying. So of course that in order to see or in order to study something very, very tiny, we need the ultimate microscopes. And as I said already, accelerators are the ultimate microscopes, and that's why we use accelerators as tools for our research. Let me say a few words about accelerators. I said that our field of particle physics really drove the development of accelerators. Now, these accelerators now are used in the world everywhere. In fact, about 30,000 accelerators in operation in the world. Of course, the big and complex ones are discovery science, like particle physics and material science, to nuclear physics, and so on and so forth. But there are many small-scale accelerators used in the industry. For example, more than 99% of tires or the surface were treated by accelerators, shrinking tubes or any wrapping materials, etc., national security, energy and environment issues, and medical diagnostics and treatments. So all of these are used by accelerators. So you can imagine the impact of accelerators to society. Let me tell you a few examples, in particular Fermilab's the involvement in how we transfer our technology, in particular accelerator technology, to industry and society. I mentioned that accelerators are used for medical treatments. Proton accelerators often now used for cancer treatments. In fact, there are about 25 such accelerators in the world in operation. The first one was in the Loma Linda Hospital. And this accelerator was designed and built by Fermilab scientists and engineers at Fermilab. And then we moved that to Loma Linda Hospital and show them how to operate and how to commission. By doing so, we already transferred our technology to industry. And right now, it's all built by industry. Another example is one of our accelerators called the Tevatron. That the accelerator required this long, a lot of superconducting material and wire. In fact, what we needed is about 2.5 times the Earth's circumference. That much long superconducting wire was needed. And at that time, the technology we had was kind of making small scale, but not that large scale. So we had to bring industry to the lab and again, work together with them. By doing so, they learned how to make the superconducting wires. So that's technology transfer. And of course, industry is very good at how to make a lot and cheap. So that has been very successful. Because of that, the MRI is affordable by the hospital because MRI needs a superconducting wire for that machine. And that's how this technology transfer is made and how society benefits from that. Very recently, Illinois State recognized the importance of accelerators. So they are supporting the building called the Illinois Accelerator Center. So with that money, we'll be able to construct this beautiful, powerful-looking building. That together with our existing infrastructure and facilities at the lab, we are now creating this center for accelerator science and technology, education, training, and most importantly, enhancing partnerships with industry. So we have a very exciting program in the future, and that center will be complete in a couple of years. So now I said accelerators are like ultimate microscopes, but accelerators are also like time machines because they make particles last seen at the early universe. So the universe started with a very, very tiny, with a high temperature, extremely high temperature, extremely high energy, and has been expanding more than 13 billion years. So we live over a very, very cold temperature. And this kind of the universe we are living in, so these accelerators can produce or make particles which do not exist in nature in abundance right now, but existed more than 13 billion years ago. So in fact, we can create the particles when the universe was age of 1/100th of a nanosecond after Big Bang. So that's very cool. This is really cool. So how we do that? We start with the proton beams, for example, and accelerate and fire at a target like that, and that produce a bunch of particles like pions or kaons. These kind of particles are produced. And by the way, particle like a kaon decays into a neutrino particle and muon. So that's how we also make neutrino beams and muon beams, etc. But this process also can create particles like antiproton. This is antimatter of a proton. And this kind of antiparticles do not exist in nature in abundance, but existed a very early moment of universe. That's why I can call time machine. Not only that, now you can make an anti-proton beam and also a proton beam. You can have head-on collisions. That's what happened at the Tevatron at Fermilab until last year. That's the machine Tevatron shut down the September last year. And also, as I said earlier, the proton beam and proton beam collision can happen also. That's what's happening at LSC. So when these beams of particles and the other beam of particles head-on collision, what really happening is it's not the proton-proton collide or proton-antiproton collide, but particles, elementary particles, who are inside of the protons and antiprotons or proton-proton. These particles make protons, right? It's like up quark and anti-up quark. That's what real head collision happen. So if particle and antiparticle collide or meet, what happens is they annihilate, so they disappear, but what's left is the energy that they originally had. So if you have a very high energy particle to begin with, we can create a lot of energy from that collision, the process. And Einstein said E is equal to mc squared. So E here means energy, and m means mass of, let's say, elementary particle. C stands for the speed of light. So what it tells us that if we have a lot of energy, then we can create a very, very massive elementary particles. Such massive elementary particles, again, do not exist in nature in abundance right now, but exist in the very early moment of universe. So the heaviest particle is called the top quark, which was discovered at Fermilab by the Tevatron Accelerator. And that mass is about 175 times hydrogen atom. So it's a very, very heavy, yet it's very, very tiny. It's not made of anything smaller. It itself is the smallest things. So that's a very fascinating particle it itself. So such massive particles, their lifetime is extremely, extremely short. So as soon as we make quarks, top quarks, let's say, then just they decay away immediately. Lifetime of such top quark is 10 to the minus 25 seconds. That's like nanoseconds. So as soon as you make them, they just decay away and decay to more ordinary elementary particles or etc. So of course, we build a detector around that and to catch all of these particles. And by analyzing each of these particles, we can figure out, it was a really top quark created by this collision. So that's how we do. So this is one of the experiments called the CDF experiment and CDF detector of Tevatron. That's the scale of the detector. If I stand up there, I look this small. So this is quite gigantic. And this is another detector at the Tevatron. If I stand up, I look like that. So this is also quite big. And of course, as I showed earlier, Atlas and CMS, these are even bigger and more complex detectors. Because Tevatron and CDF D0 detectors, this started operating 1985. So we have been running like 25, 26 years before shutdown. And compared to LSC and Atlas CMS, these experiments and the accelerators are much more modern. They started from 2009. So it's not surprising that these experiments and accelerator are more powerful than Tevatron. So this is, again, CMS detector. So I want to show this chart. This is all elementary particles discovered by modern accelerators until before the LSC start operating in 2009. Here, the size of disk is proportional to mass. So as a comparison, this is the mass of the hydrogen atom or mass of a proton. Okay, that's the size. You can see top quark, as I said, very, very heavy. Bottom quark is also heavy, but it's about 5 times of the proton mass. So Fermilab discovered top quark and bottom quark, and one of the neutrinos, the tau type neutrino was discovered at Tevatron, at Fermilab. So 3 elementary particles were discovered there. And charm quark and tau lepton and muon neutrino, these were discovered at SLAC and the Brookhaven National Laboratory. Now in European side, the gluons, this one carry strong forces. So this was discovered in Germany, and a laboratory called the DAISY. This has no mass, 0 mass. And W and Z, these particles, or we call WZ bosons, these are the particles that carry weak forces. And these 2 particles were discovered at CERN early 1980s. So you'll see that, first of all, the particle mass is all over the place. So one big question in our field is that how these particles acquire mass. So what is the mechanism? So that's how the Higgs is kind of related to this issue. Yes? Photon, I didn't put that in here because photon was already known before our modern accelerators. And photons is one of elementary particles, and photon has a 0 mass, does not have any mass. So one of the questions is how these particles acquire mass. And we think that the Higgs is responsible for giving mass to these particles, and that's what we are looking for. Another question is that even if we discover Higgs and explain how these particles acquire mass, we still don't know how this top quark mass is, what the value it is. Electron mass is equal some value, and who determined that? That's actually also a deeper question, and Higgs itself cannot explain. But first step is a finding in the Higgs and understanding how these particles acquire mass. So one thing that, okay, so going back, all these particles that we discovered and also we studied their properties, based on all those studies, we create this so-called standard model of particle physics. So this is the present theory of particle physics. And we, based on their properties, we make this chart. There are 6 kinds of quarks, and there are n-type particles, but they are not in this chart. To be simple, I just show only the particles, not n-type particles. 6 kinds of quarks. There are 6 kinds of like electrons, but they're cousins, and we call them leptons. And then there are force carriers that I briefly mentioned, and Higgs is actually the only particle that hasn't been seen in the standard model. So this actually is a really powerful theory, and if I call this as an accomplishment of 20th century, this analogy in the 19th century will be the periodic table of elements, and this is a breakthrough for understanding all chemical properties of all the elements. So I said that earlier, up quark, down quark electrons, these make all of us, and also said that there are other elementary particles do not exist in nature, but exist at the very early moment of universe. So these particles, up quark, down quark electrons, doesn't matter which atom you pick, element you pick, if you look really inside, they are made of these 3 particles. And then, of course, they are bound by forces. So this, to me, is very, very fascinating. They look very different. Their properties, chemical properties, are very different. But if you really look inside, they are made of 3 kinds of elementary particles. So it doesn't matter it's Einstein or my cat or a chair or anything you can think of, it's made of these 3 particles. So it has been quite successful, this theory and our accomplishments. And many, in fact, most of particle experimental results beautifully fit in this framework of standard model. As I mentioned, that one question we have is how these particles acquire mass. We believe that Higgs is responsible, at least within the standard model framework, Higgs is responsible for that. And indeed, that is the only particle in the standard model yet to be discovered. But as I mentioned, there are other questions. Higgs mechanism or Higgs particles cannot explain why top quark mass is the 175 times the proton mass. They cannot explain. So there are more to do. There are other questions more deeper which cannot be explained by standard model. For example, there are 6 quarks. You ask why 6, why not 4? If it's just 1, life will be much simpler, but 6 is an awkward number. Why is that? If you look at their properties, we can actually line or align like one family property and second family and third family. There are some structure there. It's like kind of family structure. And there are 3. You ask why 3, why not 2? That's another deeper question that standard model cannot answer. Now, regarding forces, like the magnetic forces or weak forces, using our accelerators, and we can go to very high energy environment or early universe environments, and these forces become one. That's very, very interesting. And if you study a strong force, they also look like the other ones when we go really high energy or early universe timeline. So big question is whether all forces become really one, like a gravitational force, electromagnetic, and weak and strong. So that's a big question. It appears to be, but we have to prove that. More than that, if a gravitational force is included in the force unification, we have to have extra dimensions of space beyond the 3 dimensions that we live in. That's very strange too, but certainly that's expected if we believe in the unification of forces. Whether there are or there exist extra dimensions or not, that's another big question. Now, neutrinos, these are very fascinating particles. We know, by the way, standard model thought that neutrinos have a 0 mass, but it turns out neutrino has mass. So that's something that's a failure of standard model or a shortage of standard model. These neutrino particles has a very, very small mass, about 1 million times smaller than electron mass, so you can see how light they are. Not only that, of course, they also oscillate from one kind to another. For example, if you can imagine me and Alan oscillating I become Alan and he becomes me, that would be very weird. But they do. They change from one, and then after a while become another kind and come back to, we call that oscillation. So we get to now learn a little bit about neutrinos, but there are many things that we don't know about neutrinos. So that's another very, very rich program and exciting area that, in fact, the Fermilab is right now quite focusing on this area. Another interesting thing about neutrinos, in fact, there are so many neutrinos in the universe right now. There are more than 100 trillion neutrinos zip through your body every second. Do you feel that? No, it's not. So they are very elusive. So they go through, but you don't feel anything. And because they are very, very elusive, they do not really interact with any matter. But there are many of them. In fact, if you count all the neutrinos in the universe right now, we can say for each electron or each proton that make all of us, there are billion more neutrinos. So if you add all the neutrinos all together and weigh total mass, I said the neutrino mass is really extremely small, but because there are so many, if we add them up, that total mass of neutrinos in the universe is about the same as the all mass combined in the universe, all the galaxies and dust all together. So that's very incredible. So we believe that neutrinos really make a big impact on how this universe is structured. So if you want to understand the universe, we must have to understand the neutrinos. Now, there's another problem. It's an antimatter problem. You know the universe is dominated by the matter. So we are all made of matter particles. But when we do experiment with the accelerators, when you collide the proton-proton or proton-antiproton, we create a very high energy, high temperature environment. There we see that same number of the particles and antiparticles. With that, we can conclude that at the very beginning of a universe, when universe is extremely high temperature and high energy, must be a similar amount of matter particles and antimatter particles. But now we don't see any antimatter in the universe in abundance. So something happened, all the antimatter disappeared, it's gone. So that's a big question. Another question is that we believe that there are a lot of many astrophysical the evidence that some kind of matter that we haven't seen yet exists. One, the example is that evidence is that if you look at the galaxy, which is rotating, that all rotation comes from gravitational force. Now, if you combine all the stars and dust in that galaxy and calculate rotational speed, that's way too small compared to what we really see. In order to explain that speed, rotation speed, we need some kind of matter 5 times more than ordinary matter. So we don't know, so we name it dark matter, and we haven't seen it. That's why we call it dark, because we haven't seen it, so it's dark. So as I said, it's everywhere in the universe. If you go to underground, it's still there, and anywhere in the universe, we believe it's there. As I said, a factor of 5 times more mass than the ordinary galaxies and all the dust combined. And we are looking for that dark matter. This cannot be explained by standard model. Another question is it's about the nature of dark energy. So I said that the universe has been expanding. In fact, it has expanded very rapidly, and then it has been continues to expand, but we thought it might be slowed down a bit, the rate of expansion. But about 15 years ago, scientists discovered that actually the rate of expansion is accelerating. So that's the last year's Nobel Prize for that discovery. So the acceleration of this expansion could be something due to some kind of energy that makes this kind of acceleration. Or it could be our lack of understanding of gravity. So whatever that is, this is the big question, and we are going after. So remember, so we start with this kind of very simple but very deep questions. But about last century, we made a lot of progress. But the more you know, the more you don't know. So we have now specific questions in 21st century. Here are the list. Understanding the origin of mass of elementary particles, why there are so many elementary particles, why there are 3 kinds of families, whether all forces become one at very high energy and high temperature, whether extra dimensions of space exist. Neutrinos, we began to understand these fascinating particles, and we have quite many things we don't know about, so we have a lot to learn from them. What happened to antimatter, what's the nature of dark matter and dark energy. So these are the 21st century questions in particle physics. Now I'm just tell you a little bit more about the first question, origin of mass. So I showed this chart of all the elementary particles having different kind of masses. So in the standard model of particle physics, our understanding is the following. If you start with a space in the universe, you pump out everything, so we make a vacuum. So if there's nothing in the universe in the vacuum stage, then all of these elementary particles do not have any mass. So they have a 0 mass and travel with the speed of light. However, if a vacuum that consists of some fields we call Higgs fields, and quanta or particles associated with those Higgs fields are called Higgs particles. If these Higgs particles are in space everywhere, these elementary particles, as soon as they are produced, they interact with these Higgs particles and Higgs fields in space. Through these interactions, somehow they acquire mass. Depending on how much they interact with or collide with the Higgs fields, the mass value of this particle is somewhat determined. Like electron does not interact with Higgs field but little, acquire small mass. Like a top quark, which has a lot of interactions with the Higgs fields, acquire huge mass. And that's how we can explain about this mechanism for these particles acquire mass. Now, searching for these kind of Higgs particles, again, if this Higgs particle is an elementary particle, we believe that's the case, then we should be able to create them using accelerators with the same process that I told you about earlier. So this search has been going on many decades. It's probably 4 or 5 decades. The most recent ones were the Tevatron and Fermilab at the LSC at CERN. Tevatron, as I mentioned, started operating in 1985, discovering top quark and many other achievements. Ended 2011. We are still analyzing the analysis of all the full data set. So final results about Higgs and other the physics coming, probably complete in the next couple of years. And LSC started taking data in 2009. In terms of the collision energy, LSC right now is about a factor of 4 larger than Tevatron energy. So they have a more powerful in terms of creating more massive particles, including the Higgs particles. And LSC, it's really international collaboration. By the way, Tevatron is also very international collaboration. We have about 25 countries collaborating with us. Really made a huge contribution of how big collaboration works and how the complex detectors and accelerators work. So our, actually, the achievements really itself is a big contribution for the next generation of accelerator like LSC. For LSC, we also have contributed the designing and building and operating some pieces of accelerators there, and then also large component of the experimental part, detectors in particular, were our contribution and many the US institutions' contribution for the LSC. So standard model, I said that the Higgs is predicted. However, this theory cannot tell you the mass of Higgs particle. So for us, it would be, if standard model has told us where to look for what Higgs mass is, life would be much easier, but doesn't tell you any information. So we have to look for Higgs, could be very light, could be heavy. So we have to have a really wide range of search approaches needed. However, there are some ways to find out what Higgs mass might be using for example, very massive particles like a quark, top quark or W particle or Z particle, because these heavy elementary particles carry information about the Higgs boson. So we did that, in particular at Tevatron. We created a top quark. In fact, at Tevatron, up quark from proton and anti-up quark from anti-proton, they collide, annihilate, and create a lot of energy, and that produces a pair of top quark and its anti-particle, anti-top quark. And then that decays immediately. So you'll see that this is one top quark. The candidate in our detector sees many, many particles, traces here. So we have quite many of such particles, of such events with the top quarks included. And with that analysis, we were able to measure mass of top quark at the level of 0.5%. And similarly, W boson can be produced from the proton and antiproton collisions. In fact, the up quark and anti-down quark could create a W boson. That decays also immediately to electron and electron-type neutrino or muon and muon-type neutrino. And using that analysis, we can also measure very precisely W boson. And right now, we are measuring at the level of 0.02%. So with that information, we concluded that Higgs mass is less than about 150 times the proton mass. Remember, top quark mass is about 175 times the proton mass. So with that information, what it tells us that Higgs is somewhere, a bit below top quark mass, but certainly heavier than W boson mass. So now, how to produce Higgs at the Tevatron or LSC? So gluons, which are particles carry strong forces, and they are also the inside of proton or inside of antiproton. So in this case, gluon collide, create Higgs, or the up quark from proton and anti-down quark from either proton or antiproton, they collide and make a Higgs and W. So that's how we can create or make Higgs particles at LSC or Tevatron. Of course, we don't know in standard model, as I said, that it could be the mass at the level of W, or it could be much heavier. But nonetheless, I just want to repeat that prediction or expectation was Higgs mass somewhere between W boson and top quark mass. nonetheless, when you really search for Higgs, we just put expectation aside. We want to look for everywhere possible. So we look for even Higgs much heavier than top quark or much lower than the W boson, etc. Just want to show you that this is a simulated event in the CMS detector featuring the appearance of Higgs boson in the detector. So these two particles, they are the daughter particles of Higgs. Like other like top quark or W boson, Higgs also lives very, very short. As soon as you make them, you just decay. But life of discovering Higgs is very, very hard because it's not that Higgs particles the showing in your detector, but there are many other particles associated with that. Therefore, fishing out Higgs is incredibly challenging. So not only that, depending on what Higgs mass is, they decay into different kind of the daughter particles. If Higgs boson mass is about 500 times the proton mass, they likely decay to 2 W particles, but also can decay to 2 Z particles or a pair of top quark. If Higgs boson mass is about 50 times the proton mass, they likely decay to a pair of bottom quark. So depending on what Higgs mass is, the final state or daughter particles are very different, so that is also challenging. So what's done so far is that Tevatron looked at around this area and also around this area. Most importantly, LSC looked all this area and searched for Higgs, and they didn't see it. So we excluded this area and that area, meaning we looked at it and we concluded Higgs is not there. So that's the yellow sort of shaded area. So with that, allowed area is this white band here. That is actually consistent with our expectations. So far, looking good. More than that, actually, we saw some hints where this, the white allowed region. First of all, Tevatron show some hints. I don't want to go through details because this is relatively complicated. So this kind of bump here above this line showed that there was some hint of Higgs at the mass of 120 or 130 times the proton mass. That's exactly where we are kind of expected. And Atlas and CMS, their bump is even more strong than Tevatron. You can see around 125 times the proton mass. Both experiments show some bumps. So that's very, very exciting. Now, question is, can we claim that we discovered Higgs? Not quite yet, because that bump is there, very, tantalizing. But there is a small chance that this could be a statistical fluctuation. Therefore, we have to wait a little bit longer, at least a year or so, to get more definite answer. Now, if you discover Higgs, that's not the end of the, all this program about Higgs or research. It's because first we have to discover, and then we have to ask whether this Higgs is what we think they are. I told you that depending on what Higgs mass is, they decay different, the daughter particles and with the different rates. We have to really study to make sure that's consistent with what we expected. In fact, the Higgs decaying to pair of bottom quark is a current strength of Tevatron, and Higgs decaying to either 2 photons or 4 leptons are current strength of LSC. Of course, LSC can do all of this very well when they take more data. So one other question is that Higgs, yes, it can explain why quarks and electrons and muon tau particles acquire mass, but they may not explain how neutrinos get their mass. So I want to remind you again the mass ratio of all the elementary particles. In this time, I want to show the sort of relative animal weight. So this is a kind of, again, chart, but, based on their mass. This top quark, let's say top quark is like a whale in terms of their weight. Then electron is like rabbit. So it's about 100 times the difference between rabbit and whale and top quark to electron. Now, neutrinos, if electrons' weight is like rabbits, then neutrinos' weight is like ants' weight. So that much lighter, so about 1 million times lighter. But that's kind of our understanding. In fact, we don't really know exactly how much neutrinos weigh. So we know neutrinos have a mass, it's non-zero, and we also know neutrinos are extremely light, but we don't know how light they are. What's the value of the mass? We don't know that. Not only that, these neutrinos, I said, are very fascinating. We believe that if you study neutrinos, all properties and behaviors, by the way, their behaviors are very different from other elementary particles like quarks and the electrons or muons. They do very different behaviors. So we believe that they might have a hint why the universe is matter dominant, what happened to antimatter. So that's another reason that we are going after this neutrino. So this is a Tevatron, this is a Fermilab accelerator. Some people worry that we would be closing the laboratory, but you shouldn't worry. We still exist. We still have a very, very strong program. In fact, we are running about 9 accelerators simultaneously until 2011. And then when 2011, when we shut down, this ring was shut down, of course, one of the biggest one. And there's a couple more, the accelerators were shut down. But most of the accelerators are still running. In fact, we have the world's most powerful the neutrino beams. In fact, we have 2, one going through here, another going through there. But these all lines representing currently operating accelerators. I don't want to go through not only the neutrino experiments, but also we have the powerful beams for other the particle physics experiments as well. So I said that there are 2 powerful the neutrino beams we have at Fermilab. These beams, actually, we are sending through Earth all the way Sudan Mine in Minnesota. It's about 450 miles away from here. Another beam line, we have a neutrino experiment on site. So I'll show you a couple of experiments going on. We are sending neutrino beam from Fermilab to this old iron mine in the Minnesota, Sudan Mine. So 735 kilometers or 450 miles. From here to there, it takes only 2.5 milliseconds. So as soon as you make them, you just get there. And we have a number of experiments here and there studying neutrinos. In fact, the neutrinos oscillate from one kind or another. We create one kind of a neutrino, so-called a muon-type neutrino. By the time you get there, it kind of changes to something else. So that's what we are going after. It has been running this particular experiment from 2005. Right now, we are building new generation of neutrino experiments to answer even deeper questions about neutrinos. That one will be operating from the end of next year with even the power is doubled compared to what we have. And we are also planning, so these are kind of this decade's experiments. While we are running, we are also preparing this next generation. We like to have a new the detector and new beamline, etc., running 2020s and beyond. So this case, our goal is that putting this more or better and more larger the neutrino detector in the old gold mine in the South Dakota. So that's the development plan going on. I just want to show you also how big that detectors are. So this is a current experiment. If I stand up, it looks like that. And this is the construction going on. And you see the person compared to that. This length is about half of football, this field. So you can see how a gigantic and massive detector is. In fact, this is a photo we took last Friday. This is me, and this is a part of one end of the experimental hall. And in fact, from here to all the way, there will be half of the football field. So I mentioned that the LHC and Tevatron has done a lot of studies of original mass, but they have very broad, rich program, can answer some of, not all of them, addressing some of these questions, and neutrino going after these questions, and also what happened to antimatter. But not only these experiments are needed, but we need actually more other kinds of experiments beyond the LHC, Tevatron, or neutrinos to really answer all of these questions. And so the Fermilab is going after some other kinds of the particle physics experiments. For example, we are now building up and creating very powerful muon beams for muon experiments. And then we also plan to update or upgrade our accelerator for, again, operating the plan for 2020 and 2030s. The so-called Project X is our development stage. That Project X replaced a very old accelerator complex that I showed you earlier. This has been running about 40 years, and if it becomes 50, 60 years old, it's time to replace with a more modernized accelerator. So we are going to replace old accelerator injector with a more powerful and flexible accelerator, and also relatively the young accelerator components, of course, we utilize. So we have a very, again, powerful the accelerator in our development plan. We also are doing dark matter search and dark energy, the exploring with collaborating with many other institutions in the world. For example, dark matter, we are developing very special and cutting-edge technology detector and build this kind of spatial detectors, putting in underground, detecting dark matter. And we also built, again, together with many collaborating institutions, 0.5 gigapixel, very, very the low noise and powerful digital camera. We put that in the Chile. Why Chile? It's because it's dry and high altitude, so this is a very good place to observe dark energy. So that's why we did. And then we also built, together with collaborating institutions, experiment called the PROJ. This one is to explore ultra-high energy cosmic particles. Again, we install and these detectors in Argentina, again, take advantage of the area. So all of these experiments we are doing in particle physics, this chart shows from Big Bang to the universe expansion and very cold universe sitting here as a thinkers. As I mentioned, that all these tools enable us to really create the conditions at the very, very early universe. I said up to 100th nanosecond after Big Bang, but we want to go even earlier because we believe, again, there are enough evidence for our belief, is that at that kind of high energy and high temperature environment, the laws of nature is much more elegant, much more complete. So this will be more complete and elegant than standard model. If we find or discover such a theory, all the questions we have can be explained much more naturally. That's why we are doing that. So far, what I've told you, and I tried to tell you a little bit about what's going on at CERN and Fermilab, what the CERN and Fermilab might discover in the near future. But more exciting thing is that we expect something unexpected. I told you about all the questions. Of course, answering all those questions, very, very exciting. But maybe something that we totally unexpected, as that would be even more exciting. We expect that we'll learn a lot about the origin of mass and what happened to antimatter and etc. But we may find new dimension of extra dimension of space or new symmetry that control the universe. And this is really exciting moment for us, for I hope all of you. And this excitement let us keep really going on. And thank you very much. Right. I didn't really go through exactly how we reach high energy. So certainly the LSC has a certain energy we can reach, right? The other particles like neutrinos and muon beams, etc., that one also reach very high energy in different ways, not the same way. it's more not direct way, but more indirect way, and we can reach energy even many orders of magnitude higher than an LSC can reach. Again, this is indirect and not direct, so that's that difference, but this enables even go much higher energy. So other tools can let us go much higher energy. But talking about kind of LSC type of thing, direct the reach of high energy, there are a lot of the technology development going on. So I don't think this is the end of the field. And we are smart people. There are many brains together. I'm sure there'll come out something, affordable. One thing is that this kind of the proton-proton collider, if you really look at the elementary particle inside, they carry about 1/10 of proton energy. So in fact, the maximum energy you can reach is based on how much elementary particles carry. So there are other kind of accelerator, the colliders that we are thinking of, either electron and its antiparticle positron collider, or muon and mu plus and mu minus collider. These are elementary particles, but we can perhaps get up to a few tera-electron volts of the energy. But effectively, this is a quite high energy than the other ones, because the proton-proton is, again, the elementary particles carries much less energy than proton. So this is a different type of the accelerators being planned. And of course, we watch for all the costs and et cetera. And our goal is, again, trying to develop these technologies to get us even higher energy with cost-effective way. Mm-hmm. They are all discrete. They are the elementary particles. That means that they are not made of something smaller. So they are all different. So if properties are also different, not only masses are different, but the quarks have their intrinsic spin, like 1/2 unit. Higgs boson has a 0 spin, and neutrino has a 1/2. And neutrino, their electric charge is 0, null. And quarks have intrinsic electric charge. Depending on what kind, they have a different. Some are plus 1/3 unit, the others are minus 2/3 unit. So these are all different. Higgs has electric charge is 0. So all these are different. In fact, I told you about all the 4 forces may become 1 at very, very high energy. Then, of course, the laws of nature are much simpler because we have to deal with the 1 force, not 4 forces. But we believe that all these elementary particles, there are many, if you go really high energy, these will also start from 1 or 2 kind of particles, not many. So that's another thing that we are going after. We go much higher energy. We may see only 1 or 2, not 6 quarks. Yeah. Right. So from this kind of the accelerators, that's way too far. So we cannot reach that scale with the current, this particle physics with the accelerators. We cannot reach. That's way too far. Although there are some experiments called the holometer at Fermilab that's kind of trying to probe that scale because anything. The word is again holographic argument. Again, this is some people may not believe in all that, but there's actually quite interesting experiments going on at Fermilab trying to figure out whether we can get to the Planck scale with this holographic the idea. How do we measure spin? So if you have this, for example, some particles, I said it has intrinsic spin. It's not exactly the spin that we are talking about. It's not really spinning, but they have intrinsic property and similar to what the spin property. That's why we call spin. Depending on what kind of spin each elementary particle has, they sort of, they are daughter particles. Say one particle decays to something else. And if you look at how they decay, with that kind of these studies will enable us, tell us that what spin this elementary particle might have. So just depending on what spin, this is how the daughter particles' behavior or properties look different. So that's the way of distinguishing spin half per the particle versus spin zero particle. Right. So I didn't really go through. The standard model is very, beautiful and intellectual construction. As I said, it has a lot of limitation. So that more complete, more elegant sort of theory using more bigger symmetry argument. So that's the supersymmetry you mentioned. So this the theory. That theory expects or predicts many kind of particles, also kind of partners to standard model particles, and that has been that search has been going on, and so far we haven't seen any evidence of particles that belong to supersymmetry. That doesn't mean supersymmetry is not right. Supersymmetry is almost like a framework, depending on what kind of parameter space you you have very different sets of particles expected. So that search will keep going, but so far we haven't seen anything yet. Right. Right. It's different. And neutrinos, as I mentioned, that among all the elementary particles that I described, neutrinos are least known their properties. So there are many ways of finding out different kind of the properties of a neutrino. So the diabe is, in fact, that, thanks for pointing out, they actually measured one of the key properties of a neutrino. So that was very, very important in particle physics. And everybody, the world was waiting for that specific measurements. So that is using electron-type neutrinos coming out of reactors. So that's a really reactor-based experiment, and that specific properties best measured by that kind of experiment. What we are doing is different kind of properties of neutrinos. So it's very, very orthogonal. So there are many more to learn about neutrinos, so that the world is really focusing on, diabe is one of them, and Japan is working on it. We are working on it. Europe's trying to really beef up the neutrino, the facilities, including accelerators and detectors, etc. So it's a very exciting area. It's a very different kind of measurements we are doing. Mm-hmm. It's probably more dark. The Higgs is related to dark energy. So because dark energy, again, that can be connected to, we could say if Higgs is here in space everywhere, and we can ask how much energy the Higgs could provide, perhaps that could be linked to the dark energy. The only problem is that if you calculate all energy, assuming Higgs in space, then it's about 62 orders of magnitude difference between what we can calculate from Higgs versus what we measure from the accelerating universe. So right, so I think if Higgs is not the kind of the dark matter, it's more relevant to a dark energy question, except that if you calculate, there's a huge discrepancy. But one thing we believe is that what we think, potential the dark energy could be something to do with the so-called field, but it's a similar kind of Higgs, but not Higgs. So there's one kind of, again, I'm stretching too much, but perhaps that field that associated with the dark energy, because this is a so-called property, the scalar field, and Higgs is also kind of scalar field, might be able to mix these two. So if you study Higgs field, maybe some clue to dark energy, but I don't think this is a very convincing argument, but people are at least talking a little bit like that, about connecting Higgs field to the dark energy, but not much with the dark matter. I think that means that this really breaking standard model, and a lot of theorists will be excited because again something that they expected but they really did, it's not there. So that creates in some sense a lot of excitement of what they have to go after. On the other hand, always finding something is exciting. So we did all the work and we got null results. So that's a little bit, again, the intellectually exciting, but emotionally that's very dissatisfactory, I think.
Well, I'd like to thank Professor Dr. Young-Kee Kim. Personally, I'm delighted that we have people who are of caliber Young-Kee trying to answer the questions of where did we come from and where are we going. So, thank you very much.
Thank you.